Hey everybody, this set of notes is about free energy. There is a set of notes in Schoology for you to use or take your own notes. You know the drill. Okay, constant reminder as we go through the second part of this unit. One, that as we talk about a chemical reaction, two big things that we always want to talk about are thermodynamics and kinetics. Again, kinetics tells us how a reaction happens. It deals with mechanisms and rates, happens with what happens before or between the beginning and the end of the reaction. Thermodynamics, however, talks about if a reaction happens, in other words, is it spontaneous or thermodynamically favorable, and the beginnings and the ends. In other words, what is the equilibrium position? What is the overall enthalpy change of the reaction? All right, so we have defined what we mean by entropy of a particular system or situation. And so when we talk about chemicals, we actually have a set of standard entropies that we can use, okay, that are well known and well defined. Standard entropy is the entropy of a particular chemical under specific conditions, under standard conditions. So we know standard conditions to be 298 Kelvin and 1 atmosphere of pressure. But there's one extra thing that goes in here, and this is having 1 mole of the substance. So when you have 1 mole of a substance at 298 K and under 1 atmosphere of pressure, you can end up with a measurement of what the entropy is of that chemical at that state. Okay, so those are molar entropy values of a substance in their standard states. And you can find those in a table like this one over here. Okay, a couple things you'll notice that the entropy of a particular chemical will increase with increasing molar mass. Okay, this makes sense because as you have more molar mass, you have more electrons, more particles, etc., that can be moving around and in different locations. And so as a result of that, you end up with more microstates, and so you end up with a higher entropy. They also increase with increasing molecular complexity. Okay, if you think about these 3 examples that we've got down here, not only do they have more mass, but this propane has more entropy than this methane, a higher standard entropy. Why? Well, you can think of all of the different motional changes that can happen here, right? All of these ends here can rotate on the propane. We also have a whole bunch of different bonds, many more bonds where we can have vibrations going on within the molecule. So again, way more microstates possible for a propane molecule than a methane molecule, and so you end up with a higher standard entropy. Right? And since we have a table then of measured standard entropies for different substances, we can go ahead and we can estimate this entropy change for any particular reaction in a similar way as which we were able to calculate delta H in previous units based on standard enthalpies of formation. Okay, so here, if we think about the standard enthalpy change of a reaction, we can calculate that by taking the enthalpy change or the enthalpies of the different products and multiplying those by the coefficients in the balanced equation, and then subtracting the standard enthalpies of the reactants, again, times the coefficients. Okay, so just another way of estimating, in this case, the standard entropy. All right, so with that set up then, we run into another interesting consequence of entropy. Okay, so if we think back to the second law of thermodynamics that we talked about a few days ago, again, it says that thermodynamically favorable processes lead to more entropy in the universe. Okay, things in the universe tend toward entropy. Well, if we define the universe as the change in entropy in the system plus the change in entropy in the surroundings, we can write an equation that looks like this. The entropy of the universe change is equal to the entropy of the system change plus the entropy change of the surroundings of our system. That would make up the universe. Okay, we know that as something happens, there is a greater probability of the disordered state if it's left alone. Okay, but we've added this little piece in here now. And this is going to be important to us as we move through our discussion today of free energy. And we'll get there in a second. So again, takeaway from this one is that the delta S of the universe tends to increase, and thermodynamically favorable processes contribute to that. Okay? So if we have a thermodynamically favorable process, delta S of the universe is going to increase. Second piece that we need to have in place before we talk about free energy is this idea that heat that flows into or out of the system changes the entropy of the surroundings. Okay, so if we think about it this way, if I have a reaction which is exothermic, that is going to move heat out of the system and into the surroundings. Well, if the particles in the surroundings are now moving faster, what have we just done to their entropy? Well, we've done to their entropy, we've created more microstates, and you have a positive change in entropy for the surroundings. Okay, so positive state change in entropy of the surroundings is heat flowing out of the system and is exothermic. Likewise, if a reaction is endothermic, heat flowing into the system, so that's going to make the surroundings more ordered as the particles cool down and don't move as fast. And so as a result of that, the change in entropy of the surroundings is going to be negative. The other thing that's helpful for us to understand about temperature is that the magnitude of the change in the entropy of the surroundings is going to depend upon the temperature of the process. You can think of it this way. At high temperatures, the surrounding particles already have a fairly high entropy. So as a result of that, any changes that would happen as a result of a little of heat flow would be relatively small. Whereas at low temperatures, the overall entropy of the surroundings is relatively small, and so heat changes that would change the entropy of the surroundings are going to make a fairly big difference as to what's going on. So you get a large change in the change in entropy of the surroundings. Okay, so in the end, since delta S surroundings depends upon heat flow, and heat flow we classify as the change in enthalpy, exothermic, endothermic, that means that the change in entropy of the surroundings is proportional to delta H at a constant pressure. All right, so taking those ideas that we had from before and adding and bringing them together, we will add one more idea here. And then one more idea is that spontaneous processes can be used to do work. Things that are thermodynamically favorable, we can use to go ahead and transfer energy. So how much energy can we transfer? In other words, how much work can we do? Well, this guy, Josiah Gibbs, comes along and he says, well, I've been doing some fancy math and I think I've come up with an equation that's going to help us understand how much energy can be used to do work or how much energy is transferred in a particular process. And that amount of energy, or that energy that can be used to do that work, is now known as Gibbs free energy. Okay, and we can go ahead and quantify this using the equation that the change in energy, or in other words, the amount of energy transferred, is equal to the change in enthalpy minus temperature times the change in entropy, okay, of our system. So where did that equation come from? Well, in your book, you can read about it, but essentially they took the second law of thermodynamics, that things in the universe tend towards greater entropy, and substitute delta S surroundings using expressions of T and delta H related to what we just talked about in the previous slide. We can derive out this expression. If you're interested in how that comes about, you can go ahead and read in the book very deeply. All right. So what you do need to know, though, is that, as we said, and as we learned in our POGL, the delta H term is very, very closely related to the change in entropy in the surroundings. And the delta S term, of course, is the change in S in the system. Okay? So if we think about it this way, this over here is about the change in entropy in surroundings and system, which we know is the change in entropy of the universe. So through some, again, manipulation, we can see that any time that the entropy of the universe is positive, delta G is negative. Okay? Therefore, knowing what we know about things that change the entropy of the universe and their spontaneity or their thermodynamic favorability, we know when a process is spontaneous or thermodynamically favorable, delta G is negative. So this idea then leads us to a better understanding of why some processes that are endothermic can be spontaneous or thermodynamically favorable, even though their delta H is positive. Okay. So let's look at the delta G and what happens to that as we talk about different temperatures. Okay, so let's go ahead here and let's just kind of think about it. What is the sign of delta G if, first of all, delta H is negative, so that would be exothermic. And if delta S is positive, that means that entropy is increasing. So if we look at delta G, that's going to equal a delta H, which is negative, minus T delta S, and delta S is positive, so that means that this term is going to be a negative and adding more negative to that, right? So this overall, my delta G here is going to be very, very negative, which means that this system is going to be thermodynamically favorable, and it is going to happen, okay? What happens if delta H is negative and delta S is negative as well? So we've got exothermic in this case, but this time we have a decrease in entropy going on. So delta G in this case would equal negative plus a negative T times a negative delta S. Well, that's going to be a positive. Okay, so now in this particular case, in order for delta G to be negative, the delta H term has to be greater and the delta T term has to be smaller. Well, what determines that? It's going to most likely be this T term over here. So at this particular case, delta G will be negative at low temperatures and positive at high temps. Okay. What if delta H is positive, endothermic, but delta S is also positive? We have an increase in entropy. Okay, so that delta G is going to give us a positive minus T delta S, and delta S is going to be positive, so the second term here will be negative. So again, this will happen. This delta G will be negative at high temperatures, because that will make this term very, very big, right? And it will be, delta G will be positive at low temperatures. Okay. What happens if delta G is endothermic and entropy goes down? Well, in that case, delta G is positive minus T delta S, but delta S is negative, so that's going to end up making this whole term positive. So we've got a positive and a positive, and in this case, delta G will always be positive. This idea then is summarized in this table that we've got. For the table, free energy changes, you can see the different aspects of entropy, enthalpy, as well as the T delta S term, and what then happens to delta G. So again, if delta H is negative and delta S is positive, that is going to be thermodynamically favorable at all temperatures. If we have the opposite, delta H is positive or endothermic and the entropy is decreasing, that will be not thermodynamically favorable at all temperatures. If they're both negative, that will be thermodynamically favored at low temperatures and not at high temperatures. And the opposite is true as well. If they're both positive, it will be thermodynamically favored at high temperatures, but not at low temperatures. All right, So in terms of calculations, a lot of this is just understanding what the signs, different signs of the terms in the Gibbs free energy equation happen. But we can also calculate free energy for any particular reaction. Okay, so this is just like enthalpies of formation or standard free energy the standard entropies we saw earlier. So if we go ahead and we think about the standard free energies of formation, this is delta G of F. This is in Appendix C in your textbook. It's also on that green sheet that I gave you a while ago. So in this particular case, the delta G of F, again, it's a standard condition situation. So 278 K, 1 mole of the substance, 1 atmosphere of pressure. And if we're talking about solutions involved, the solutions would need to be 1 molar solution. So those are all conditions that need to be satisfied for us to be able to conduct an estimation using standard free energy changes. But from there on, it's the exact same thing. Delta G is going to be the delta G of formation of the products minus the delta G of the formation of the reactants with the coefficients from the balanced equation factored in. Okay, so thus we can do the same kinds of calculations and reaction manipulations for delta H as we do for delta H. So anything having to do with Hess's law. So if we reverse a formation reaction, we change the sign. If we put multiples of coefficients in front of the formation reaction, we then once again multiply by that coefficient, whatever the delta G of formation is. All right. Last thing that we have to talk about here is some reactions in nature are not thermodynamically favored, but we still see them happen. Okay, and the way that they happen is they get coupled with a spontaneous reaction. So basically, what you end up with is that the delta G of the favorable reaction ends up being greater than the delta G of the unfavorable reaction in magnitude. Okay, and so as a result of that, you can use the free energy from the favorable reaction to then power the unfavorable reaction. One of the most common ways we see this occur in biological systems is through the processes of cellular respiration on one side. So if you go ahead and you take glucose and turn that into carbon dioxide and water, the energy that is released, free energy that is released in that process, which is thermodynamically favorable, can be used to take a phosphate group and add it to ADP to make ATP. So this process is unfavorable. Well, then we can take our ATP, and turn it into ADP, breaking that bond, and as a result of that, you get that's a favorable process. You can use the energy for that to then drive other life processes, like taking simple molecules and turning them into cells and cell constituents and things like that. So again, favorable processes to power unfavorable processes, favorable processes to power unfavorable processes. So that's it. Those are the basics of free energy and understanding Gibbs free energy. Go ahead and make sure you add summary and questions to your notes. Thanks.